Hi, everybody. Thank you very much for joining. For the ones of you that have seen the Lira introduction that we've done before on the main stage, there will be a bit of repetition for a few ones that haven't been here, but we're going to drag in much more deep into the elements and the coding part and how this language was actually built. So let's just start without further ado. So as mentioned before, we build a language that allows you a secure execution of financial contracts on the blockchain. We'll run quickly through the layout. We mentioned before the market for derivative is huge. It's $500 trillion. I'm going to run quickly through most of the stuff. We mentioned it's way bigger than most of the other markets that we know, the gold markets, the world GDP, which is just a fraction of the size of the OTC markets. But move a bit faster because we're not capturing the same as before. One of the main advantages, in our opinions, for using smart contracts are exactly this one. You can remove intermediaries. You can create a transparent value that can be cleared for trade reporting, and immutable handshakes that can be seen by both parties on the contract. As we said already in the previous talk, one of the biggest challenges within these smart contracts are the underlying security risk that sits in each one of them. The security risk is really, as this code is exposed to cyber security risk of attacks, is exposed to bugs, and many other issues that we've seen before. The two most fundamental examples we know are the DAO hack, roughly $150 million under attack, and that was at quite low valuation of it. Today it will be on the billions. It was 8% of it in circulation, and the party wallet bug that made stock $280 million. But the point is that this is really the tip of the iceberg. 45% of contracts on the Ethereum network, based on the research by Loi Lu and some others from Kyber, are having some vulnerabilities issues. So that was our main issue in terms of building Lira, where we want to create a language which is easy to program, but is also really, really safe. We ran through a quick example here. I'm going to move a little bit forward, but the main point here is that the code you see upstairs here, the 6th line of code, is formally verified contract language that actually creates that derivative, 10 Bitcoin to 555 Ether, in 3 months' time, running from today to 3 months' time. This is the same technique that is used, formal verification, for secure and real-time system that cannot fail, like airplanes. We may not love it if our airplane has to be restarted while we are on the air. May not be the best experience we have had. And on top of that, the fact that we created a separate language allows us to connect it on verticals of a variety of blockchains. The hard work has been actually working as a language, and now we can write compilers to a variety of blockchain. Our first one is working on Ethereum, compiled directly to EVM, so we can actually run the code directly there, no need of solidity in between. But we can move it to other interfaces. And again, if you can imagine, writing code for a future on Ethereum, on Solidity, will be hundreds of lines of code with quite large security risk. And we can write the same future with Lira in 6 lines of code on formally verified language. So another implication of that is that because future contracts start in fair price, the future contract we've seen before in the example discuss 10 Bitcoin to 555 Ether, it started with a specific exchange rate, which means unlike other DeFi applications that require over-collateralization because the counterparty can run away with your funding, right? If I loan you $100, if I haven't taken at least this amount in other collateral, you may run away. In this case, the contract started in a fair price, so you can only keep this additional 20, 30, 40% for the risk management side. So let's go quickly to an example of utilizing the language. We're going to take Rapid, and we're going to trade. We're going to trade 2 Rapid to USDX, eToro currency. Let's pick two ones, for example. For this example, we have an exchange rate which is taken, while usually you create this future contract 1 month ahead or 2 months ahead. These are the most liquid one. For this example, we run it in 40 seconds. We can create the contract, and upon the creation, it will be deployed. In this case, we run it on a testnet, and when it's deployed, we can actually execute it and see the code. Let's start by seeing the code of the contract. You can see here, I'll try and get closer to it. All right. You can see here there are both, so there are two operations that are happening here. We scale the amounts because there are quite a lot of digitals when you look into at Satoshis, but we scale a transfer of one token in the upper side. It's the token representing the USDX. Address of the token, in a second it will be more clear, so forgive me for the binary side. And on the other side, we have the two wrapped hits and the transfer. You can see that the counterparties are switched here, which also means the language is multi-party. We can take it back, and we can approve the contract. See that we have 998 wrapped hits. So once the transaction is signed, once the approval is happening, then we will likely see two of these hits removed to sit in the collateral from the other line. We wait for the activation. It's a bit difficult when you run it on testnet. You actually need to connect to the, it is in progress. The two hits are down, so we have 996 here. And once the contract is finished running in 40 seconds, we'll be able to see the transfer of the USDX back to our balance here. While it is executing, I'll mention that in the next stage, we're actually going to look a bit into our GitHub and we'll really discuss how this language is being built. So we're going to get much more in depth here in comparison to the previous one, if you've seen that before. So let's just wait for that to be finished. We see that the yellow line refers to the time has passed. Now it's waiting for execution on chain. Then it will turn green once we get a confirmation. Now the UI will take a couple of seconds and it changes. Let's move to our GitHub now. So we're back in the Lira GitHub, open source. A comment before that, there is no hidden token here in the ecosystem. It really is open source language, and really appreciating getting as much as possible feedback to us on how to better communicate it, how to initiative connection to other different protocols, and how to make the usability. We have the resources to actually help allocating it. So let's go quickly through it. So here is the Lira language. And before getting into depth, into the full definition of the language, I will walk you quickly through a couple of examples. As you probably have seen before, wow, it's a bit hard to see, but eventually a transfer, and the insight we had when we built this language is that financial contracts are a list of transactions. And each transaction is a transfer of some value that can be tokenized, in our case, an ERC20 token, or representing whatever, between two counterparties, which are two addresses on Ethereum, one of which could be easily a contract, right? So the transfer operation is really, if we look upstairs, as an asset, which is what you transferred, an ERC20, and two parties, P1 and P2, which are addresses. And eventually, everything going to turn out to be a list of transfer in the language. That insight allows us to make a non-Turing complete language, which means the language itself can be goodly or good formally verified, and we can get really nice properties of that. Then the next operation is scaling, because this transfer is, of course, atomic, but it's just one asset is transferred, and you want to create sort of a value with different numbers. So as you may see here, it's a bit on the side. Scale has a bit, the first parameter scale take here is an asset, is how much is going to be scaled. And there is a limit to the scaling. We'll show it a bit more in a second, which comes from the fact that you have to have two issues, right? You have a transfer or a contract in the end of it. We'll go to the specification in a second of the syntax. You want to have a limit of how much you need to actually put in your deposit, in your margin account to cover for that, because here you can decide what kind of element of risk management you want to put into the system, and you're going to have the amount of assets you scale it by. Let's go down a little bit. And here we'll look into the real syntax of the language. So let's look first at contracts. Everything we build eventually are contracts that are executed. So a contract, the leaf operation, is either a zero contract, which means do nothing, die, or a transfer, which we talked about before. These are the only final operation of anything that happened. Then you can use a scale in order to say, I don't want to just transfer one Bitcoin, I want to scale it and do 5 or 4.2 or whatever. You can use both when you plug in a couple of operations together, and you can also identify them to become atomics and under some setups. You can use the translate, which just means wait time, because these are contracts in the future. And you have if within, which is kind of important to issue optionality. So if you want an example of an American op, you need to allow a period of time by which you can call the option or you can execute that. We'll go back to that in a little bit. So the stuff we've seen there before are mainly constructs, but you can see we also have expressions. Expressions are really essential because they are numbers in our system, and also they are representing observable. Observable are a way to get oracles and information from the real world and from a variety of spaces into our language. This is essential for running the executions. And you can see in the expression that we also have E1 operation E2, which means if you have two expressions, you can run an operation between them. Or in the binary case, you can have one operation of that. Let's look at the operation quickly. It's what you would expect of them, nothing special. Plus, minus, multiply, and so. If is also an operation we initialize. And we have or and end, and we can create not on the unary operation. Going back, we have time. Time can be now, where it's referring to a direct execution, but it can also be transferred to a time unit, U of n, and the units we support are seconds, minutes, hours, days, and weeks. So you can actually utilize it for that. Also, that's very easy for us to add more of these if required. The next point to show is that we have different types of operation, which are either integer or Boolean, but I think we can move ahead right now. We're changing computers? Oh, we have done already. Okay, so let's look a little bit into code. So the first code here is really representing what you guys have seen before. We have here an example of a future contract. In here, we want to run it for 1 second because there is no reason for us to wait that time. And we scale to have 100 USDX on one side, and on the other side, 100 DAI. I'll go back a little bit in details, even though it's repetitive a bit. So again, the final operation, we transfer DAI from counterparty to me, when these two are addresses that we're going to operate locally. And we have 100 transfer and 100 limit. So it means we actually require that the margin will hold 100. We can change this number, obviously. On the other side, we have a scaling the same thing exact with USDX, which is the eToro stablecoin of dollars, therefore exchange rate of 1 to 1. And we use both to put both operations together and to run together. The last point is we have translate for 1 second because we want to make a future 1 second ahead. Let's talk about how it runs.
Yes, I'm Peter, and let's try to make this practical. So the first thing I'm gonna do is actually try to run this contract and execute it manually. So the first thing we want to do is to compile this future we see on the left side. So let's define it. We have the compiler here. We say Lira future. That's actually the one that I have on the left side. So this is compiled, and it will automatically also deploy it. So now we have an actual address on the chain. This is run against a local chain. So the first thing we're gonna do is now that we want to approve the different margins. So the first one is from me to my counterparty, let's say it's Omri, and we want to approve the 100 USDX over here. So I contact the USDX token and say that the contract that we just deployed are allowed to spend 100 tokens on my behalf. And that's a success, even though it looks not like it, but it is a success. And then let's do it again. So let's now, this time we want to do it from Omri to me, who's the counterparty. So let's try to, and he has to approve 100 DAI to the contract as well. And so what I do now is I approve it on the DAI. Again, I make the contract allowed to spend it on Omri's behalf. And again, this is a success. So before I want to activate it, just want to show that Omri has 1,000 DAI. I have 1,000. And Omri has 1,000 US dollars. And the same with me, as you can guess. Okay? So let's start by activating it.
Just
And-
one word.
Yeah.
The reason why approve and activate are separated because we need both counterparties to approve it.
Yes.
And we don't want to withdraw the money away from your contract before you see that all other counterparties have approved that.
Exactly. So now everybody has approved their limits. So I contact the contract and say activate. Simple as that. Boom. And this is a success as well. Oh, it is not. 2 seconds.
As mentioned before, actually, and the difference between the approve and the execution and activation,
There we go.
if one side didn't approve in this case, you couldn't actually run it.
Exactly. So that shows that it won't work if no one is approves. So now it succeeded. And if I look at the balance of Omri's DAI, it's now 900 as we would expect, and the same with me on the USDX. And just to be clear, and I still have 1,000 DAI. So what we expect is that the DAI will now increase by 100 when I execute the contract, as 1 second has elapsed, as we show up here. So let me do that. So it's a contract, execute, and it returned successfully. And we now check that my balance has been increased by 100. Yes. And woo. And just to make sure that Omri got his part as well.
I hope so.
I hope so too. Yes, he did. Yeah. Okay.
All right.
So now let's go for the next
Let's take another
example.
example because you've seen the future one. We want to take another example a bit different because it's very versatile also for OTCs. Let's look into an option, actually an American option. I mean, I'll challenge a lot of people to be able to write American option in 6 lines of code, and actually one of them has just the word 100. You can actually write it in 2 lines of code. So what actually happened in American option, just for everybody here, this is an American put option. So look, the important line is the max line. It says, we're going to pay, in that case, 100 minus the price of Ether. So it means if Ether drops below $100, you get a put, you can get it for $100. So you get the difference in the price between $100 and Ether, because you have your Ether as well. So it's a very common and simple financial derivatives. So what does it say? The payout is max of 0, because option will always have the optionality to use it. So it will at least worth 0 for you. Or 100 minus the observed, which again take us back to the Oracle, getting the information as to the change of the price feed of ETH to USD, because we compare ETH to USD. Then we will have it into a scale. So this number can be 0 if the option is out of the money, which will mean, let's look at the operation again. We settle this amount in USDX. So we have transfer USDX from me to the counterparty. How much will we transfer is based on the max. It's based on this calculation. It could be 0 if the option is out of the money. It can be 10 or 20 or 50 if the option is in the money. And we have 100 for our margin requirement, if you remember the specification. And again, we'll wait 1 second with it, but you could do it 90 days, 30 days, whatever you want. Please, Peter.
Yes, so now we'll run this example. Okay, so let's start by compiling it as the same as we did with the future before. And let's say Lira compile, specify the path, option.lira. Up, and we need an wait here. Okay, so now we compiled it and deployed it. Again, we can verify that it has an actual address on the local chain. Yes. So in this case, we want to approve 100 USDX. So that means that I has to approve these 100 USDX as I am the party here. So let's start by doing that. So USDX approve. And this time we use the option address that's allowed, the option that is now allowed to spend on my behalf, and 100. Yes, that went through. Okay, so first we just want to show you that the price feed, which is from an external oracle, in this case it's our own contract, is actually right now at the moment, with the USD here, it's 100. So that's the price.
Right. So right now, if the option would be executed, you will be paid 0, right?
Exactly. So now that we have everything in order, let's try to activate and begin the contract.
You want to change the...
No, I'm going to activate first.
All right, you activate it first.
So now it's activated. So now I'm manually changing the price, but you could imagine this could come from different place. So I'm now setting it to 20. Boom. And now when I first, let's just check that our balances is as it should be. So let's check that my balance is 800 from before, and it had took 100 in collaterals. So 900 from before minus 100 is 800. And now that I want to show that Omri has an 1100, same as before. Okay. So now that the price has lowered to 20, we should now expect that Omri will receive 80 USDX. So let's try to execute it. Yes, it went successfully through. And I'll check Omri, he's got 1180. And I actually got the 20 back. Even though that I put a full 100 in collateral, I got 20 back as the price went down to 20.
Yeah, so just to show the easiness of it, I would also ask Peter to move back to the American option and say, this American option was missing something or not missing something, you never paid for it. You got it for free. And if someone said, maybe we want to write the code that will actually initiate the buying of the American option, so you can add another transaction, will actually do. You do both, because you want to have all the execution that used to be in the American option, as well as a new transfer which is buying this American option. And yeah, you scale this by the price of that. In that case, we pay $5 from the counterparty to me, and that's it. Now you added a payment to it. Really simple. You can easily imagine with a variety of both. I can create a loan with 30, 36 payments. It's fairly easy to use, at least in my opinion. That was the main stuff we wanted to actually show to you, but we actually wanted to ask if anybody want to participate, ask us anything. And apart from it, to say that this stuff is open source. We're going to have 2 hours workshop in DevCon if some of you are coming there. A bit more in-depth about tools on how to build in it. And we would really love to get feedback from people from the community on this formally verified language for financial contracts and the execution and how you can find it useful for you. If anybody want to ask a question, we are happy to take one.
Okay. You can hear me, right? Yeah, so I have a question. You've built a language which is non-Turing complete for building financial products, correct? So my question is, how do you think... yeah, thank you. Do you think it will be useful at all, given that you can't have loops in your language? For example, let me just elaborate a bit. So I want to build some lending application. So people can throw in their Bitcoin and then work on this. And of course, you need loops for this to do payouts and other stuff.
So first, very good question. I want to elaborate on two things related to it. First, I'll answer at your question. So the answer is a clear yes, because the insight we had into financial application is correct to the one you said, are that they are finite time. There are 30 payments. Even if I want to take a mortgage for 30 years, I pay monthly for it, 360 payments, and it's done. 30. And the second point is that, I don't know, you probably have more experience than me writing code with functional languages, but you can actually, and this language is clearly functional, I mean, I didn't discuss it in details, but you can actually create, I would call it macro-like effects with functional languages. It's really clear that you don't want to do a loop the way that you can create loop in a Turing complete language, which means while loop you can't do, but there are ways to create a for-like effects in such a language to make the development easier. We can take it off stage about how you do it specifically. Back to the Turing complete discussion, we see it as an advantage.
So is this just an internal DSL? It's okay now? So it looks like an internal DSL. It's just a function call with arguments. It's not clear function call in which language. Maybe Solidity. I'm not sure. JavaScript. But still, why do you call it? It's a smart contract language. It's just a function call.
Very good question. First to identify, there is no solidity. We use our language, we run a compiler to EVM, i.e. to the bytecode of Ethereum. We tried in early stages to do it with solidity. Was not a great idea, at least from our experience, with all due respect to that. It's also open to a lot of security risk. The second link is simplicity is really the key of what we're doing here, because we talked about the security of running the contract. The hard part of this language is not the specification of the language, it's the formal verification of the language. We took a couple of years of work of postdocs and PhD to actually build it up. Also, we share some of the paper related to that. So the hard part is really to make the language secure. It's the whole discussion of DSL against multi-purpose, right? And I'm personally in favor of DSL, especially in execution in time-critical software. It's both easy to develop and also super secure. But also we want to have stuff from the community. If there are stuff missing in it, maybe we can extend it. It's a different projects. If there are other elements into the community, we can contribute and make it more easy via libraries to support it. So we would love to have discussions on that. Last question before we are torn away. Okay, thank you very much. It was a pleasure to talk to you guys.